So I have an interesting setup over here. I have a magnetic field that is constant, and it's going straight out of, as you can say, the surface of this loop. The magnitude of the magnetic field at any point of the surface is going to be B. And what's interesting here is this loop that we have, this right part of the loop, is movable. You can imagine it's a cylinder here that can roll to the right. And the magnitude of its velocity, we're going to say, is lowercase v. And this cylinder, let's say it has length L. So given that, you can see that we're going to have a change in magnetic flux. Why are we going to have a change in magnetic flux, or a change in magnetic flux through the surface? Well, if this thing is moving to the right, when its speed is v, it could be any units, meters per second or whatever it is, you're going to, even though the magnetic field itself is constant, you're actually going to be changing the area that is, I guess you can, contained by this loop. And so that is going to give us a change in flux. And if you have a change in flux, that is going to induce an electromotive force, or it's going to induce a voltage in this loop, which will cause a current to flow. So let's think about what that electromotive force that's going to be induced is going to be. And I'm just going to rewrite Faraday's law right over here. Faraday's law, negative N times our change in flux. And we're talking about our change in flux over change in, let me write that a little bit neater. Our change in flux over change in time. Now the n is the number of loops we're talking about. So in this case, n is just going to be 1. And the negative, I've already complained a little bit about it in previous videos. This is really just reminding us, the math, when you're not using kind of proper vector mathematics, this just reminds us that this EMF is going to cause a current to go through this loop, and the magnetic field that is induced by that current will go against the direction of our change in flux. So that's just something to remind us there. So what we really care about is our change in flux over change in time. So what is that going to be? Let me just write it here. Our change in flux over change in time. Well, our change in flux in this case is going to be our change in the magnitude of our magnetic field that is going perpendicular to the surface times the area of our surface over our change in time. And what is this going to be equal to? Well, B is constant. It's not going to change over the time that we care about. So the change in B times A, it's really just going to be B times our change in area. B times our change in area over how much time goes by. So what is our change in area going to be? So let's say that we let delta t, so let's say delta t happens. What is going to be our change in area? Well, let's let delta t go on. So if delta t goes on, this cylinder, or if we wait for t units of time, or if t units of time go by. So let me do this in another color. So let me see. I have not used. Let's see. So I'm going to use this color right over here. So how far will we go after delta t? Well, we know the magnitude of our velocity. If you multiply the magnitude of your velocity times your change in time, that will give you your distance. And so your change in area is going to be the amount of distance that's traveled times the length of the rod, which is just that. So our change in area, which is that area right over there, our change in area over that time is going to be the distance this rod goes. And notice this rod is going in a direction that is perpendicular to the direction of the magnetic field. That's an important thing to realize. And so we have our change in area is going to be this dimension, which is how far the rod travels, times the length of the rod. That's how much area we gain. That's how much it increases. Our area increases. So times the length of the rod. That's our change in area. So then we can substitute that back over here. So this is going to be equal to, and this is going to be equal to, we got our B, we have our change in time, and our change in area, we just said, is going to be, let me just write it this way. I could write it as the length of our rod times the magnitude of our velocity, or our speed, times our change in time. Well, change in time divided by change in time, those cancel out. So our change in flux over that time, or our average rate of change in flux, we see simplifies to the length of our rod times the magnitude of our velocity, or our speed, times the magnitude of the magnetic field that is going perpendicular to the surface. And this is something that you will see many times in your physics class. This whole notion of, hey, if your rod going in a perpendicular direction to a magnetic field, it induces an electromotive force of LVB. Well, this is where it's coming from. It's coming directly from Faraday's law. And you could say, okay, if that's happening, what direction is the current going to actually flow in? Well, if the magnetic field isn't changing, but since the area is increasing, the flux is increasing in the upward direction. So you could say the flux is increasing in that direction. So the current that gets induced, and the magnitude of the current is going to be based on how much resistance we have, but the current's going to induce a magnetic field that goes against our change in flux. So let's see, if the current went that way, if the current goes that way, what will happen? So I'm going to take my right hand out. So if I take my right hand out, put my thumb in that direction, and if I were to loop my fingers around, this would, if we went that way, this would induce a magnetic field that goes like this, So that actually would enhance the flux going through, or the change in flux. It would go in the same direction of the change in flux. And we've already talked about this would violate the law of conservation of energy. So the current's going to go in the other direction. It's going to go, in this case, it's going to go clockwise, because the current is going to induce a magnetic field. Once again, I can take my right hand out and try to draw my right hand, and we can see now the direction my fingers go in are that way. And notice we're looking at the inside of the surface. So the inside of the surface area was increasing, so it was increasing the flux in, I guess you could say, the upward direction. We're getting more of the magnetic field in the upward direction being contained in the area. So the magnetic field induced by the current that is induced, that current is caused by the electromotive force, and the magnitude of the current is going to be dependent on our resistance. That's going to go in the other direction. It's going to go down that way. So, or it's going to induce a magnetic field that is going to go downwards. So the current needs to be going clockwise.